First of all, many thanks to organizers for inviting me to present this talk at this very interesting conference. So the topic of my talk is, yes, written there, transport model approach to lambda and anti-lambda polarization in heavy ion collisions. The work is done in collaboration with Larissa Bravina and Alexander Vityuk. Next slide, please. Yes, mainly it is based on two publications earlier this year, one in Phys Letters B, another one in Proceedings of Strangeness Quark Meta 2019. Next slide. Oh, next slide, please. Yes, introduction. So next. Yes, since the name of this session contains phase diagram, I have to show this phase diagram, and we can see that before, say 20, no, this one. Yes, 20 years ago, 15 years ago, the main slogan of our community was to go to higher and higher energies. Unfortunately, at RIC and LHC energies, we don't see the distinct signatures of the phase transition. So the community decided that instead of, say, first order or second order phase transition, we have just smooth crossover. And now we are coming back from high energies to intermediate and a little bit lower energies during, for instance, beam energy scan at RIC. And in future, we hope so that we will have two more facilities, NICA and FAIR, because this energy range provides us with still a high temperature, but also a high baryon density. And already now, during the beam energy scan run, RIC collaborations like STAR found very interesting signals and effects. Next slide, please. Yes, exactly. So I put this citation from a well-known paper by STAR collaboration published 3 years ago in Nature. The discovery of global lambda polarization in non-central heavy ion collisions opens new directions in the study of the hottest, least viscous, and now most vertical fluid ever produced in the laboratory. Indeed, what does it mean? As it was first pointed out about 15 years ago, no more, that in non-central heavy ion collisions at relativistic and ultra-relativistic energies, huge angular momentum. The system possesses huge angular momentum, especially at the very beginning, and it means that this angular momentum is transferred to very large vorticity. But then it was proposed how to measure it, that vorticity is somehow linked to particle polarization. For instance, hyperon lambda and lambda bar polarization. If at high energies like 200 GeV, the top RIC energy, the polarization of both lambda and anti-lambda is close to zero, then during the beam energy scan, when energy was reduced to up to 7.7 GeV in the center of mass frame, the collaboration found that, first of all, the polarization of both lambda and anti-lambda is small, about 1–2%, but positive first. And then if you look at this slide, at this plot, you can see that although within the error bars they coincide, but still polarization of lambda bars are a little bit higher. But when we come to the bottom point in energy 7.7, you see huge polarization of anti-lambda, about 80 or 8.5%, although with the relatively large error bars, but definitely it's say almost four times larger compared to that of lambda. And since then, a lot of solutions, a lot of approaches were proposed, and many models were used, both microscopic and macroscopic, like hydrodynamic models. Please, next slide. Yes, so what's this about? How to measure lambda polarization, and why lambda and lambda bars are very convenient particles? Because they are so-called self-analyzing. What does it mean? During the weak decay, the proton tends to be emitted along the spin direction of the parent lambda, so it's relatively easy to measure these. And then one can restore the lambda polarization vector in the hyperon rest frame. And next slide. And then the theory, actually, that's the definition of the so-called thermal vorticity. So today I will speak only about this thermal vorticity, not about any other effects related to for instance, axial current, so-called axial vortical effect. So if the system is, first of all, that's an important assumption, that if the system is in local equilibrium and the concentrations of both lambdas and lambda bars are relatively small, their ensemble average spin values S mu here, can be presented like this. So they're linked to the thermal vorticity tensor, which is written below. Yes, B mu means the ratio of for velocity to temperature. And after further approximations, please, next slide. Yes, we can separated further in the time and space components. And what was measured by the star collaboration actually is the projection of averaged spin S onto the direction of global angular momentum J. So it was the theory, and now models at our disposal. Yes, we employed a microscopic transport model UrQMD. Probably you have heard about the features of this model many times. So please, next slide. Next slide shows the production of particles via the string excitation mechanism, like HSD and PHSD, UrQMD, and like also as a shear model. UrQMD uses the Lund longitudinal excitation mechanism of Lund longitudinal mechanism of string excitation. Next slide. Yes. Another thing is that we have to extract somehow thermodynamic quantities like temperature, baryon, chemical potential, maybe even strangeness chemical potential, because out of the microscopic model we can get just energy density, net baryon density, and net strangeness density. And then we employed the statistical model of ideal hadron gas, with essentially the same number of degrees of freedom. It means the same particles as in the UrQMD, and the table of particles in UrQMD is quite rich. 52 baryon states, 30 now, it's not 32, 39 meson states, anti-states, and so forth. Because if we, for instance, in the statistical model, if we determine temperature mu b mu s, we can easily determine the partial number density, partial energy density, partial and total pressure, as well as entropy density, and then compare, for instance, yields, the first line, with with those provided by microscopic model. Next slide. Yes, that's the block scheme, how to proceed. So we extract epsilon rho b rho s out of microscopic model, then put this in the system of highly nonlinear equations, and then compare by minimizing the chi-square. Finally, get temperature mu b mu s, and at the end, so we get just a T mu b mu s of fully equilibrated system, but we have to make the final decision. It means we have to compare, for instance, particle abundances or particle energy spectra, both obtained microscopically and macroscopically, to see if our system is in the vicinity of equilibrium. This procedure was yes, developed about 20 years ago. Next slide. And now I'm coming to the results. First, we checked the conservation of angular momentum. We found that it is not conserved a little bit, especially at the earliest, not especially, but at the early stage, because of inelastic collisions. However, the deviations are within 2%, so it's a quite good accuracy. Thank you. Next slide. And then the quite important thing is that in cascade microscopic models, we don't have any mechanisms preventing the particle to be emitted from the very beginning of nuclear collisions. For instance, in hadron models, usually people are running the code until the freeze-out mode, when system is disintegrated into the particles. But before, particles are not allowed to be emitted. Here we see that both lambdas and lambda bars are emitted, although not uniformly, starting from the first collision, from the first Fermi over C. Although the here, of course, that's logarithmic scale, the maximum of the distribution, although it's a little bit smeared, one can see that it takes place between 7 or 10 Fermi over C up to 20, maybe 25 Fermi over C. And if we calculate the mean freeze-out time, you see a little bit difference. The mean freeze-out times are different, a bit of lambdas and lambda bars differs within 1 Fermi over C. So it's, of course, it looks like negligibly small, although it is not, because the vorticity of expanding system drops also exponentially very quickly with every Fermi over C. Next slide. Yes, that's, for instance, evolution of temperature and energy density. So temperature plots, that's the upper row, bottom row, that's the energy density in the transverse plane. So transverse plane beam axis, that's Z direction, impact parameter X, that's axis, that's X direction. Here, for just comparison, we took the very central collisions with impact parameter essentially 0. But you see, for instance, at the bottom plot, that the energy density peaks in the fragmentation ranges where the spectators are, and then it drops as the system expands, and especially central area becomes more and more dilute. So the behavior of temperature is also like this, although this figure, these pictures can illustrate the so-called core corona picture, where corona is quite cold, and the matter in the core is, well, especially at times between 9 and 23, it's more or less uniformly hot. Okay, Raman, we can skip next 2 slides because they show the baryon, the behavior of baryon chemical potential, strangeness chemical potential. Yes, and that's, we are coming to thermal vorticity in reaction plane. So why reaction plane, ZX? This plane is very important because it's parallel to angular momentum of the system. And to produce also our results, we calculated a little bit more than 1 million events for each impact parameter. B equals to 6 Fermi and B equals to 9 Fermi. To be within the range of centrality 20 to 50%, because Stark collaboration published the results obtained essentially for this centrality being 20 to 50%. So we took a little bit more narrow interval. Yes, and the whole volume of expanding fireball was subdivided into the smaller cells. And for each cell, since in the microscopic model, we can trace any particle back to their last interaction point, either inelastic or elastic, it doesn't matter. So we can, from here, we can find the area when this particle was emitted, and then calculate the temperature as well as baryon and strangeness chemical potential of this area during at the time when the particle was emitted. And thermal vorticity component presented here, that's for low energy, 7.7 GeV. At higher energies, this thermal vorticity has the typical quadruple structure. Here we still see the blue areas in the third and fourth quadrant with a negative vorticity. So it means that here polarization is positive, and with slight like a stride or bottleneck between them. This stride appears when we are coming down with bombarding energy. So, and this connection part becomes smaller when energy increases. Next slide. Here we have spatial distribution of lambdas, both lambdas and anti-lambdas. And that's another important point, because you see when the bombarding energy drops, we can't get rid of the influence of spectator regions. For instance, at higher energies, at LHC or top Rig energy, These spectators are flying away, so when we are studying the mid-rapidity range, we don't see any difference practically between a lambda and lambda bars, because the matter in the middle is almost baryon free, or at least net baryon free. Here we can't get rid of the influence of the spectators, and lambdas can be produced easily out of proton, whereas to produce lambda bars, it's practically impossible. Next slide. Yes, so here two examples, distribution function of lambdas and lambda bars, and you see that these dark red points on the upper two plots, they show the regions of the maximum lambda and lambda bar emission. The emission takes place between roughly 7 and 20, maybe 25 Fermi over C. Next slide. Yes, that's for high energy 62.4 GeV. Here the distributions are more, much more symmetric one, these emission functions. Yes, next. And then the polarization. You see, because of the higher vorticity at the early stages, the polarization of both lambdas and anti-lambdas emitted within, say, first 5 Fermi over C is really very high. It can be easily, say, 60 to 70%. Although it drops exponentially, so after 10 or 15 Fermi over C, this polarization of both hyperons is negligibly small. But the problem is that since lambda bars are emitted in average a little bit earlier, so 1 Fermi over C here in the plot matters. It results in higher polarization. Next plot. Yes, and that's our main result, our main plot. So we compared our calculations obtained for lambda bars in gold-gold collisions at energies from 200 GeV up to 7.7 GeV with two impact parameters, 6 Fermi and 9 Fermi. And you see for calculations below, starting from 64 GeV, no, 62.4 GeV, we see that polarization of lambda bars is a little bit larger than polarization of lambdas. So the band, the green line and the blue line, they show us the band of polarization of lambdas and anti-lambdas respectively. And we can see that for lambda bars, we can, for the impact parameter 9 Fermi, we can get the polarization about 3%. Also remember that some people claim that 50%, that's the impact, 50% of centrality means impact parameter 10 or even 10.4, 10.5 Fermi. After that, we can get easily something like 4% for polarization of lambda bars, so no problem. But please remember this line, blue line on the top, up to 3%. And next slide. Yes, here the left, upper left plot, that's the comparison which I took from the nice review paper by Francesca Beccatini and Mike Lisa. Unfortunately, you see, when they put our results, the hadron cascade, the magenta line, they took the very bottom line, which corresponds just 20% of centrality, not even 50%, because remember, our line hits at 7.7 GV hits 3% and can be increased as, for instance, in the parton cascade calculations within the AMPT model, the people, as I told you previously, they used 10.4, 10.5 Fermi centrality, so very peripheral event, and in this case, also our results will go up. Although to hit 8%, I must admit that to hit 8%, it's not so easy. On the other hand, our idea with different, at least first our idea, with different freeze-out times was considered to be quite interesting and reasonable. And our friend Laszlo Cherney, together with his two Chinese collaborators, Yilong He and Gang Chen, they picked up these and used in their hydrodynamic particle in cell code. You see the right plot when the freeze-out times were fixed. That's one difference between lambda bars and lambda polarization. One, when it is variable freeze-out, red dots, red circles, you see this difference increases to almost 2.5. So that's quite reasonable. And then I'm coming to the conclusions. Next slide. Next. Although conclusions are rather conservative. So first four, that's more or less like technical. So the method of calculation of lambda polarization transport model is developed. But the main physical conclusion, that's the last line, that freeze-out of lambda and lambda bar is different in both in space and in time. So these hyperons, they're emitted from parts of the system with different vorticity. And also this result is nice and important because it doesn't contradict and it doesn't criticize any other effects. But it means that the baseline or background of this effect should include these different freeze-out times and different space of particle emission. So you can top your effect on the, you can put your effect on the top of this baseline and then even increase the polarization at lower energies. Okay, so I'm done and thank you for your attention.
Thank you very much, Evgeny. I see already one talk. Please don't remove slides. We will need it. I see one question in the chat. Could you please go to slide 22? Could you tell, please, what are the two small peaks in polarization plot of AA collision and later correction to vorticity plots? Yeah, here. No, next. 22 page. Next.
Oh, I cannot see the numbers. I don't know. So.
But it was two vorticity plots with the peaks. Next. Yes.
Here, probably.
Here.
Yes.
Just what is the origin of the peak? The question was.
What's the origin of the peak? No, you see, you mean the top, yes? That's
yes,
just,
I assume yes.
That's just time. Time when it was produced. So time ranges from 0 up to 100. And then vorticity in the reaction plane, vorticity of lambda and lambda bar, which are emitted.
Okay.
Well, and after that, the color shows us, imagine that that's the projection of our hill on two-dimensional, yes, projection, and this color bands, they show the main concentration of both hyperons.
Okay,
according
thanks.
to their according to their vorticity.
I don't see a hands, and I think thank you, Evgeny.